which is way better than just electric by itself. And like always, especially when we get into here, it's really, really hard to analyze the magnetic without calculus. So all like Isaac Newton, whenever he started working on physics, he invented calculus because there's no other way to solve physics. You need calculus to do physics. And previously, everything we've done up to this point, we had an equation for it. We don't have to use the physics. We just derive that equation once using calculus, and then we use that equation for it. Magnetic, though, is not the case. Every single situation, after you solve the calculus, you get a new equation. So every situation is going to be 100% unique, which means lots and lots of equations because we don't have calculus in high school, at least not in this. So where do I want? See, I can't even give you. Let me actually show you Maxwell's equations of electronegativity. Maxwell's equations of electromagnetism. I didn't upload that. There are four seemingly simple equations. Oh, I don't like this notation. Let's see if I can actually find. Because I used the letter D. So it's the del dot product with the electrical field. The del, it's not del, that would be Laplace. Let's see. I'm trying to look up or remember advanced calculus. Laplacian is squared. What do I call just a single one? Yeah, it is del. I think it's called the divergence. Yeah, the divergence. In this case. So the divergence of the electrical field is equal to some constant. The divergence of the magnetic field, which is represented by letter B, is equal to 0. The curl of the electrical field is equal to the partial derivative, the negative partial derivative with respect to time, the magnetic field, and the curl of the magnetic field is equal to this. Note the J is, you don't need to really write this down. This is high level advanced calculus. So integrals. To give you a brief overview of what integral and derivative is. I think I've done this before, but I'll just remind you. Let's say I have some curve. If I were to take an infinitesimally small delta x right here by some infinitesimally small delta y, so rise over run, I get the slope. The slope of this line is equal to the derivative of this function, and y is equal to some function x. If I integrate, so you can think of derivative as being slope. If I integrate this function f of x with respect to x, and let's do it from this point here 0 to this point right here, I'll call B. Or yeah, I'll do it from here. So I'll call that A. So from A to B, I would get the area under this curve. This would be negative area. So this is represented by the area. This is your ordinary calculus 1 and 2. However, Maxwell's equations are done with vectors. And it is ultra complicated. It is line integrals. It is dot products. So we saw how to add up vectors. And it's not very. The most simplest thing you do with vectors is add them. And we saw what we can do with it. If you add up two vectors, you can make a parallelogram. And you get the result. You take the components and add them up and do it together. Multiplication is, there's dot products and vector products. There's two different ways you can multiply them together. But you're doing it over an entire line or something. It's very complicated. Some of them have no solution. Or no algebraic solution. Meaning that there's no possible way to solve it using algebra. And then there's the line integral versions of it. And where you have an arbitrary line of vectors and solve these equations. It's very complicated. And the question is, which equation, because there's going to be a tremendous amount of them, should I start with? So every single shape is going to give you a brand new equation for. There's no simple equation for magnetism. It actually depends on geometry. I guess I'm going to begin with this one. Let's begin with force. So, a moving charge in a magnetic field and we represent with the capital letter B is a vector field, experiences a force. So let's say that I have a magnet. So let's say that I have a south side of the magnet. And I have over here a north magnet. Thing about know about magnets is there's always going to be a north and a south side. So that means over here will be south too. But the magnetic field is going to point from north to south. You can think of north as positive, south as negative. It's just how we find it. So this is going to be our magnetic field. And let's put a small positive charge in it. Then the force experienced on this particle is going to be equal to the charge, Q, This is a scalar. There's no vector on it. It's just a value. Times the velocity of the particle, cross product with the magnetic field. So this will be charge. It's a scalar. This would be velocity. Velocity always has a direction, so it's a vector. This is cross product. This will be magnetic field, which is a vector, has a direction. And then we get force. And force has a direction, so it's a vector. Do you remember the last equation we used that had cross product in it? No. That would be torque. So if we had a pivot point and we put it a force like this at some angle theta, and this distance here is r, this is our force, then the torque is equal to r cross product F. Right? Now, what'd the cross product do? Well, that's why I'm showing you to help you remind you. What only counted in this example? So, what if I tried... So, torque is rotation. What if I pushed on it horizontally? Torque was 0. So, only the perpendicular force component. So, this is the perpendicular. This would be the parallel. Only the perpendicular. So, it would be equal to RF sine of theta. Only the perpendicular component actually mattered. So, same thing here. Only the perpendicular component is going to actually contribute. And let's pull up this picture. Are you right-handed? This is known as the right-hand rule. Even if you're left-handed, you still need to use the left-hand rule. I am the right-hand rule. So, there's 2 ways of doing it. Curl your fingers. And I should say, let's assume that this is moving vertically upward in some velocity. Upward, not in. So if I draw my axis, this would be, these 2 dotted lines are your horizontal. So if you curl your fingers in the direction going from velocity to magnetic field, your thumb is going to point in the direction of the force. Another way of doing it is putting your thumb in the direction of the velocity, your fingers in the direction of the magnetic field, and your palm will be the direction of the force. So if this was shot from, like, if we had a table here and it's shot upward, what would happen is, as it's moving upward, it's going to be a force to go in another direction. So all 3 of these vectors are not pointing in the same direction. Let's see if I can get an example. So, magnetic field is going to be measured in Tesla. And let's see if I can get Tesla unit. So 1 Tesla, which we represent by capital T, is equivalent to 1 kilogram per I'll do amp second squared. Amps are amperes, seconds, kilograms. It's also equal to 1 Weber, I think it's called, divided by meter squared. Weber. And this is just flux density. You might have seen me already do something similar to this. Remember how I had this sitting here and I draw the area and I told you it's the flux going through it. This is the flux I'm meaning about. It's more complicated. We're going, so it's 1 Tesla going from a square meter. So how many Teslas are going through every square meter? And where's Gauss? 1 Tesla is equal to 1 times 10 to the 4th Gauss. So this is Tesla. This is Gauss. Gauss is, so that would be 10,000 Gauss is equal to 1 Tesla. Is the ratio. Gauss is, so it's kind of like milliliters versus liters. Gauss is just a more precise thing. Let's see if I can find Earth. So Earth's magnetic field is between 0.25 and 0.6 Gauss. A refrigerator magnet, I'll just actually, so we're going to be dealing with Tesla, but most of anything you encounter is going to be Gauss level. I don't want to put all those zeros. You can convert between it. A typical refrigerator magnet, 50 Gauss. An iron magnet, 100 Gauss. Let's see if we can get the Tesla values. So, millitesla is a refrigerator magnet. So so let's see. I'm trying to think of a good example. You know what a mass spectrometer is? So how do they determine what elements make up some chemical? Let's see if I can find it. Oh, by the way, so the full equation, this is known as the Lorentz Force Law. The full equation is this. Where this is the electrical field. We've already done F equals QE. This is the proportion for the force of the magnetic field. So if you have both an electrical field and a magnetic field, you get that. If you have no magnetic field, then this is your simple Q times E, your electrical field strength. Oh, where is it? I'm trying to find a very specific example. I want to do a mass spectrometer, but where is the... cyclotron, there it is. So what a mass spectrometer is we have a large we basically we put in some sample into it, some mass. So we're going to put some mass inside of it, and we're going to heat it up to a very, very, very hot temperature. So hot it becomes a plasma. What's a plasma?
I just know like the plasma.
Well, we have solids, liquids, gases, and we keep heating it. If it's a solid, eventually you get to the melting point. Then it'll become the boiling point. And then you get the ionization point, which turns it into a plasma. A plasma is where it's so hot that the electrons no longer stay bound to the atom. So we're stripping off. So let's look at the simple case. We have a positive proton a negative electron. Altogether, this is a hydrogen atom. Altogether, neutral charge. So no charge overall. The negative and the positive add together to give you 0 charge. If I get it so hot that the electron is no longer there, it's flown off, I get a positive charge. So it heats it up until it becomes a plasma. So we're basically giving it a charge. And then we're going to send it into a large magnetic field. The dots represent the magnetic field, where it's coming out of the paper. So dot represents a magnetic field coming out of the paper. And that'd be towards you. The notation is a dot means towards you, and X's means away from you. So we have this charged particle moving at a velocity to the right. We have the magnetic field pointing towards you. So this would be the magnetic field. So what direction would the force be in? So right hand rule. So point your thumb in the direction of the velocity, your fingers in the direction of the magnetic field, and your palm would point in the direction of the force. So thumb to the right, fingers out toward the camera, my palm is pointing downward. So that means as this is going on, it's going to have a net force pointing downward. So it's going to come over here, and it's going to be moving that way, but there's going to be a force pointing downward. So what's it going to do? It's going to start turning downward, right? So it's going to start turning downward. So now the force is pointing, the velocity vector is pointing this way. What direction will the force be pointing? Yeah, you have to rotate your hand. So thumb is now pointing, I have to rotate the paper. Thumb is now pointing to the right. Fingers are pointing up here, and then my palm would be pointing downward. So this way, right? So it's starting to turn. What shape is it going to draw? So let's stop right here. It's now doing this way. What direction will the force be in? Perpendicular. So it's now pointing this direction. Let's continue now moving it out to the left. So now the force is pointing this way. What direction would it be pointing now? Again, perpendicular. So what shape is this? Circle. It will be doing a circle. So basically, there is no electrical field. There's only a magnetic field in this example. So we have this hot gas, or plasma, I should say, that is moving inward. And we have this large, so it's going to come in here and make a circle of radius r. And it's going to hit this wall. How big is the radius of the circle? What does it all depend on? So it depends on the force. The force is equal to the velocity cross product with the strength of the magnetic field. So it depends on the strength of the magnetic field. It depends on the velocity of the particles. And most importantly, it depends on the charge of the particles. So think back to chemistry, or I should say your knowledge of 8th grade science dealing with chemistry. If we remove all the electrons, what does the charge represent? Well, I basically just said it. So let's say we have a helium atom, which is 2 protons, 2 neutrons, and 2 electrons. So it has a net charge of 0. If I remove the electrons, I'm left with 2 protons, then it would have a charge of plus 2. It's technically plus 2e, but we never include the e because we know e is 1.6 times 10 to the negative 19 coulombs. So what is the charge equal to? It's equal to the number of protons. What is the number of protons at number? It determines what element it is, right? So if we heat this up to where it turns into atoms and atoms are stripped of their electrons, then each particle that goes through this magnetic field will have a charge equal to the number of protons. So let's say, and the amount of force is stronger the more protons and charge it has. So if we send hydrogen through this, it's going to hit this wall with a smaller radius. If we send oxygen through this, it's going to hit with a bigger radius. We send something like lead through this, it's going to hit with a bigger radius. And if we have a detector here that measures the collision, what does that mean? If we send a sample through here and almost all of them hit right here, we know we can calculate what the charge of the particles needs to be for it to land right here on the wall. And that's basically what a mass spectrometer is. So this would be a basic mass spectrometer. It can basically tell you very accurately what atoms make up a chemical. So we can basically break something down into atoms, heat it to a plasma, so that they're all charged, and send it through a giant big magnetic field. We calibrate it so that if it has a charge of 80 protons, it's going to land here. And how we calibrate it basically is we send lead through it and measure the distance it lands on the wall. And we know that a charge of 80 gives us this value. All we have to do is very precisely control the magnetic field and very precisely control the velocity. Velocity is very easy. We basically have a plasma. We can have a fan blowing it and keeping it in a certain speed. We can regulate how fast air blows, or plasma blows. And we can very, very carefully regulate the magnetic field too. And thus, the only thing that changes is this Q value. So, I'm not going to know these values. I haven't worked out an example, but let's do one. Let's say that let's say that we're moving these through it at a velocity of 100 meters per second. Let's make the magnetic field equal to a half a Tesla. And let's make our Q, carbon's a good one, equal to 12E. So that'd be 12 times So 1.92 times 10 to the negative 18 coulombs. Earlier I said an amp. So an amp is equal to coulombs per second. How do you spell coulombs? This is an ampere. I never say ampere, I always abbreviate as amp. So what would be the radius of the circle it generates? So let's say we have a circle. And let's say you're in a car, you're driving around a circle. So if you're constantly changing direction, that means you have a force on you. That's the definition of acceleration, a change in velocity or direction. So we have some center-seeking force. Do you remember the equation for it? This is the centrifugal force. It's a fake force. Centrifugal force is the real one. We don't care about, so the centrifugal force of an object is equal to its mass times its velocity, tangential velocity squared, divided by its radius. And I guess you need to know that, let's see, 12 AMU in kilograms. Let's say that the mass of this particle is 1, let's just round it up, 2. It's equal to 2 times 10 to the negative 26 kilograms. So we know that the force making it go in a circle is equal to the charge times its velocity times the cross product with the magnetic field. And remember that if the two vectors are perpendicular from each other, then sine of theta is 1. And so this would be equal to Q times B times the sine of theta. But if they're perpendicular, sine of theta is equal to 1. So in this example, it's just Q times velocity, and I'll remove the vector signs times B. It's Q times B times B. So this is equal to the force, but it's going in a circle, so it has a centrifugal force equal to this force. This force is making it go into a circle. So these two values have to be equal. So that means the charge times the velocity times the magnetic field has to be equal to the mass of the particle times the velocity squared divided by the radius. Solving for the radius has to equal the mass times velocity squared over the charge times the velocity times the magnetic field. And one of the velocities are going to cancel out. Obviously, if it's not moving, it would just be spinning in a circle. And so if its velocity was 0, it would be a radius of width 0, which wouldn't be a circle. Hence, you can't divide by 0. But this is the equation for the radius. So so plugging in our numbers, and I have no clue if this is going to be a stupid number or not. So the mass is 2 times 10 to the negative 26 kilograms. The velocity is 100 meters per second. The charge is 1.92 times 10 to the negative 18 coulombs. And the magnetic field is 0.5 Tesla. So let's see if this is realistic. So 2.083 carried times 10 to the negative 6 meters. So it'd be in the micrometer range. Would be the radius of this. So basic mass spectrometer. You ionize the particles. You get, you accelerate it so they actually control very precisely the velocity. So you accelerate it to some velocity. You have a velocity selector. Basically, only allow particles of a certain velocity to go through. So you know very precisely the velocity. You know the magnetic region. And the radius is equal to mv over qb. And you're curious what a velocity selector would be. It is very simple. So we have an electrical field and a magnetic field. So if they're moving too slowly, then the force pulling downward is basically equal to Q times electrical field. So they're constantly falling downward because of the electrical field. If they're moving so like gravity. If you want, so if I throw a baseball really slowly, gravity is going to win out, and it's going to fall. If you're trying to shoot it out the window, if you throw it very slightly, gravity is going to pull it down too quickly before it makes it to the window. So if it moves too slowly, gravity, the downward pulling force, is going to make it fall downward. And the magnetic force has a velocity in it. So if you look at here, the velocity is going to, the magnetic force is going to make it go upward. And it's dependent on the velocity. If you counter these forces out equally, then it'll go in a straight line. And you have a little tiny opening here that shields it, so only particles of exact velocity are able to go through. And the velocity would be equal to the electrical field divided by the magnetic field. Makes sense. So if you have your parallel plates, this is all positive charges, all negative charges, and you put a positive charge in it, it's going to experience a force equal to Q times this electrical field strength, pointing downward. If you have, in what direction is it? North. We have a north and a south. Force is going in this direction. If the particle is moving in this direction, then we're going to have a force pointing upward equal to QVB. And if you counteract these two so that the net force is 0, maybe counteracting gravity too and plugging that in. So atoms are so light, gravity can be ignored almost.